Hi. So in this video, we'll continue our discussion on the extensive game with perfect information. Okay. So previously we had a lot of definitions for the extensive game with perfect information, and we had this example, right, using the game tree. So as we mentioned, the the strategies of the players in extensive game with perfect information would be just the contingent plans, right? So what do the contingent plans mean? So basically they mean that those as follows, as we just write in this table, right? And we also mentioned that this game could be transformed, or it could be translated into this kind of presentation by the simple form of the strategic game, right? So a contingent plan for such as mentioned here, for example, for player 1, so it could be 2-0, 1-1, or 0-2. So those are three plans. But for player 2, the contingent plans would be a combination of those different actions in three possible cases, right? So because player 2, after the histories by player 1, then player 2 has to move at either of those three nodes, right? Here, here, or here, right? So it means that player 2 has to form this contingent plan to include all those possibilities, to include all those plans as player 2 strategy for this game, right? Okay, so those three letters simply denote the different actions in each of those after each of those histories, right? So the first letter is this action here, this y, right? So this y denotes this y, and the last y is this y, right? So those are all those plans that player 2 has, all those different combinations for the player 2s to make, right? Okay, so and after we do this transformation from the extensive game into the strategic game, then we could write that down as this payoff table, right, as we did before. So we could write down all those payoffs, and then we used the red and blue underlines to denote the dominant strategies under each given other player's actions. Then we could find the Nash equilibrium, which are those. So 2-0 2-0, so those four, and this and this and this, right? So there are lots of Nash equilibrium here, right? But actually many of those Nash equilibrium are not plausible, okay? So they're not satisfactory because the Nash equilibrium in this dynamic form, or in this extensive form game, it has some problem, right? So it simply ignores the dynamic structure, or the extensive structure of the sequential game, right? Okay, so the only two plausible, or the only two reasonable outcomes are that those two, right, that we have labeled in green. So which is player 1 plays 2-0, and player 2 has a plan of YYY, and player 1's plan is 1-1, and player 2's plan is NYY. Okay, so and we can have a look at those two strategies, those two outcomes, right? So if player 1 chooses 2-0, and player 2 has Y, Y, and Y, okay. So from the perspective of player 2, okay, well, here is okay, right? Because player 2 either way gets 0, so player 2 could choose either of those, so it's fine. But here, player 2 chooses Y, of course, because this Y is higher than this 0, and here, of course, this 2 is higher than 0. Okay, so given those behaviors of player 2, then player 1 simply chooses this 2-0, because player 1 could guess this highest value of this 2 here, right? So that's pretty reasonable. But for all the other entries, all the other Nash equilibrium in the same row here, for all the other outcomes, they're not reasonable, right? Because if we have some n's, then this player two is actually not quite reasonable, right? Even if so, the reason is that the player two, if player two acts as the plan made by player two themselves, then this would be not the best case for player two, right? So, and the same for this 1-1 here. Okay, so let's just erase those underlines. So if player one strategy is 1-1, and player two's plan would be n, y, and y. Okay, so here is reasonable, and here is reasonable, but here, okay, the reason that why it has to be n is because if player two instead chooses this y, then player one could simply choose this 2-0, right? So this would be still also reasonable, and it's consistent with all the other actions by the other player, right? Okay, and you could later by yourself to verify all the other results or the other outcomes which are not implausible, right? Okay, so we could have here, from here we could have some notes. Okay, so all those are contingent plans, right? For player one and player two, right? So we have those, and also we could have some notes to say that. So all those equilibria except those two green ones, except 2-0 y. So equilibrium is just outcome, right? So do not write payoff for the equilibrium. So 2-0 y and 1-1 and y. Okay, except those. So all the other equilibria involve an action of player two, which is implausible. Okay, after some history from player one, right? And because that is simply because the player two rejects some proposal that gives player two at least one of the coin or objects, right? Okay, so so here that we could see from this comparison between the all those lots of those Nash equilibrium, but and as compared with those two green ones, right? So those two green ones are some. This is called refinement, right? Refinement of Nash equilibrium. So this would be a new solution concept that we're going to introduce now, which is called subgame perfect equilibrium. Okay, so the reason why it's called subgame perfect is because that it has more requirement than Nash. Okay, so it has to. So a subgame perfect Nash equilibrium, it is a Nash equilibrium, and also it has to be Nash inside all of the subgames. Okay, so that's why it's a refinement, and it's called subgame perfect equilibrium. Okay, so we'll also define what is called a by a subgame, right? Okay, now let's define that. All right, so definition. So a subgame of this gamma of a tensor game with perfect information and HP preference. Okay, a subgame that follows some history H is also an extensive game, right? So we simply know this gamma H, okay, and use some new notation, so still the same players, but H is given some little h, okay. So this simply means that this subgame follows some history h. Okay, that's notation for that. And the p function follows some h, history h, and the preference follows some history h. Okay. This n could be also following some history h, but normally n doesn't change, right? Okay, so where h, given some history h or following some history h, is the set of sequences h prime of actions for which actions h prime is in h. Okay, so this history h and h prime together, this is also an element in h, right? So this longer one. Okay, so that's reasonable. And this function p after following some h is defined as follows: p after some h of h prime of p equals to p of h and h prime together, right? For each h prime in h following some history h. Okay, and the preference is defined by h prime is weakly preferred for player I following h, then h double prime if and only if the history h and h prime is weakly preferred, then h double prime. Okay. All right. So it simply refers to some a part of the game. Okay. So that's called a subgame. So from this picture, we could have a very brief, very straightforward example of that. So the game itself is also a subgame of the game, okay, of the game itself. All right. So and besides that, so the other subgames could be this, and this, right? So those are three subgames, and of course the game and entire game is also a subgame of itself. Okay. So the notation of equilibrium that we just defined requires that the action prescribed by each player's strategy be optimal, given the other player strategies for every history, right? So given a strategy Si of player I and history H in the extensive game gamma, so which is denoted by the Si following H, right? Conditional H or like given H, sort of that notation, right? Of the strategy that Si induces in the subgame gamma H, right? Okay, now we could also write that down, right? So the notion of equilibrium just defined requires that the action prescribed by each player's strategy to be optimal. Okay. And this is given the other players strategies after, and this is important, after every history, right? Okay, and further, given a strategy Si of player I and history H in an extensive game gamma. So this is denoted by Si H, the strategy. So this is the strategy that Si induces in gamma H subgame, right? So essentially it means that Si following H of H prime is Si H prime for each H in this set H following H, okay? So that's essentially what it means here, okay? And we also denote this outcome as the outcome function. So that's a function, right, of this gamma H. Okay, so lots of new notations, but essentially the idea is very simple, okay? So we just mentioned that, show that in the picture. Okay, so a subgame perfect equilibrium. Okay, now we firmly define the new social concept. So a subgame perfect. Those are just lower cases, right? Not someone's name. Subgame perfect equilibrium of an extensive game with perfect information, gamma and HP preference is a strategy profile S star such that for every player I and every H, which is not terminal H, for which player I is going to move, we have okay. So it's still the comparisons between the outcomes, right? And the utilities of the action the strategy profile has a weakly higher utility than all the others in equilibrium, but this is in turn in terms of the outcomes following some history H, right, for the subgame. Okay, so OH S star given all the other players following some H, strategy profile for player I following some H is really preferred, and also this notation is following some H. Okay, interesting. And this doesn't change. Okay, and this SI is for every SIs, right? SI. In this gamma H, right? Okay, so that's the definition for the subgame perfect equilibrium. So it's just a Nash equilibrium, but it's true for every subgame, right? Okay, so that's the definition. All right. Okay, so now we're going to introduce some important result, which is called the one deviation property. Okay. Or sometimes it's called one-shot deviation, but here we just refer to the textbook. It's called one deviation property or one deviation principle. Okay. One deviation property. So this lemma or this property simply helps us to see that whether an outcome is a subgame perfect equilibrium. Okay, so basically by checking that each after each history, then the first action that each player plays, we simply need to check that for the deviation to verify that verify the subgame perfect equilibrium. Okay, and later we will have more intuitions of this result. Okay, so now let's first write those notes down. Okay, so all right, so we still have the same notation for this gamma. So this is a finite horizon extensive game with perfect information. Okay, so that's too long. We don't write that down. So we know that. So the strategy profile S star, okay, all right, is a subgame perfect equilibrium of the gamma, okay, if and only if for every player I and every history H, okay, where player I is going to move, then we have this outcome following some history H for the other players' strategy profile and player I's strategy following some H. Yes, this doesn't change. Okay, and for every strategy SI of player I in gamma H, right? That differs from SS star following some H only in the action it prescribes after the initial history of this gamma H. Okay, so now let's have a closer look at this lemma. So essentially it's saying that so in this extensive game with perfect information, so the strategy profile S star, it is a subgame perfect equilibrium of this gamma if and only if for every player and every history. So it means for each subgame, right? So for each so where this player I is going to move, then we have this. Okay, well this relation is pretty standard, and we have seen this a lot of times. And this has to be true for every strategy SI of player I in the subgame in the subgame gamma H that so this means that what is different from this SI star, so which is just this SI, right? So it refers to this. So this is a long sentence. Okay, so differs from SI star following some H only in the action. So as we just mentioned, so the first action, right? Only in the action it prescribes after the initial history of gamma H, right? Okay, so why it is true? Why it's saying that this strategy SI that differs from this SI star only in the action it prescribes after only the initial history of the gamma H, right? So why is just the is only requires the first action after the initial node, right? For each subgame. So and intuitively, that's not difficult to guess or understand, right? Because we need to check. Essentially, it already asked us to check for every subgame, right? So that should be true, right? So for each subgame, then in each small subgame, then we have that for the, so it's already split it into those different subgames. Then we just check for each first player for the player who moves first. Then we just need to check that, right? So that should be essentially true, but we have to prove that mathematically. Okay. All right. So so the convenience that this lemma brings us is that we only need to check that the first guy, right, the first player who's moving after the initial node of each subgame, right, and we do not need to care about all the later or the other actions played later, right? So that is simply because that the other actions played later will be also checked for the other in the other other parts, right? So that has to be true. So this statement. Okay, so so now let's formally prove that. Okay. All right. So if S star, this strategy profile, is a subgame perfect equilibrium of this gamma, then it satisfies the conditions, right, that we mentioned, the definition. Okay, now we suppose that S star is not a subgame perfect equilibrium. Okay, so it means that suppose that player I can deviate profitably in subgame, let's say gamma H prime, then what will happen is that there will exist a profitable deviant strategy Si of player I in this gamma H prime, for which we have SIH is not the same as SI star after this H star of H. Okay. For a number of history H which is not larger than, so we use this L as the length L of gamma H star, okay, which is not larger than the length of this gamma H star. And since this gamma has a finite horizon, since gamma has a finite horizon, so this number is also finite, right? So from among all the profitable deviations, player I in gamma H prime choose a strategy Si for which the number of history H such that the strategy profile strategy SIH, which is not equal to the strategy profile SI star, following some H prime for the H is minimal. Okay. So from among all the profitable deviations of player I in this subgame gamma h prime, simply choose a strategy Si for which the number of history h such that SIH is not SI star following H prime, H is minimal, right? Okay, then we let H star be the longest history H of gamma H prime for which we have SIH is not equal to that. Okay, then what we have is that the initial history, okay, then the initial history of gamma H star is the only history in gamma H star at which the action prescribed by SI differs from that prescribed by SI following some H prime, right? Okay, and further, SI following some H star is a profitable deviation, right? Profitable deviation in which game? In gamma H star. Since otherwise there will be a profitable deviation, there would be a profitable deviation in the gamma H prime that is different from SI star following H prime after fewer histories than does SI. Right? So SI following some H star is a profitable deviation in gamma H star that differs from SI following some SI star following some H star only in the action that is prescribed after the initial history of the gamma H star, right? Then we complete the proof of it. Okay. All right. So when we write down the notes, write down the proof, the complete proof for that, it looks pretty long, but essentially, the intuitively it's saying that we do not actually need to check all the other actions, right? So the only action that we need to check is just the initial one after some initial node of each subgame, right? Okay, so that's a lot of interesting definitions and results that we have for the subgame perfect equilibrium, and later we'll show more properties or more relevant things related to the to this solution concept. Okay, and more results.